So we have loaded our variables, we've standardized them and turned them into masked arrays for the explanatory variables. So now we're going to formulate our Bayesian model using pymc3 again, taking into account that for some of our variables we have missing observations. And actually, so let me zoom out a bit so you can see the overview of the model. The model is actually pretty much the same as we had before. So I have the priors on the coefficients. So this part from here to here is actually identical to what we had before. Nothing has changed here. The part that has changed is the part over here, so I'll say a bit more about that in a second. So here we define these new variables, which have missing observations in them. So we have GDP, smoking, binge drinking, BMI and inequality. And then when we specify the model, we use these new variables. Yeah, so the convention that I use here is that the underlying variables, GDP, smoking, binge drinking, etc., they're written all in lowercase. And the variables that take into account that there are missing values and then draw values for these missing observations, these are the ones that are capitalized. Yeah, so here GDP, smoking, binge drinking, etc. are capitalized. So these variables no longer contain missing values, yeah, because for each missing value we have drawn a value that we're going to use in our posterior distribution. And then here we actually use these capitalized versions. Yeah, so these are the versions without any missing values in them. Yeah, so the model is pretty much the same as we had before, except that we have this section here on missing variables. And then in the model we actually use these new variables which have no longer missing observations in them. Yeah, and apart from that, everything is completely the same. Yeah, so we have a new model now which we call normal missing instead of normal as we had before. But you know, here we draw the so here we do the trace. Here we draw the posterior predictive so that we can predict our the values for mortality. And here we save the posterior trace and the posterior predictive into this object data posterior, which we now call normal missing. Yeah, so I'll now zoom in again so you can read when we're actually going to look at the details. Yeah, so again, so we have with PM model S, and now we call this model normal missing. Not just normal, but we take into account the missing values that we have. The priors on the coefficients are exactly the same as we had before. So the fun is basically in this section here, which we called missing variables. Yeah, so this is new. So basically what happens here is the following. So we say that GDP, so the capitalized GDP, is normally distributed. Again, we repeat the name GDP. And it's normally distributed with a mean equal to 0 and a standard deviation equal to 1. Because this variable was standardized, so we actually know it has a mu equal to 0 and a standard deviation equal to 1. And observed, so here we use again this keyword observed, that up till now we only use for mortality, we only use for the variable that we're trying to explain. Here we also use for an explanatory variable, so we say observed is the variable GDP, yeah, which is the variable we defined above. This is the standardized version of log GDP per capita. And we do the same here, so when it comes to smoking, the fraction of people that smoke, we say it's normally distributed, we repeat the name of the variable, it has a mu equal to 0 and a standard deviation equal to 1. Yeah, so because it's a standardized variable, and again we say observed is the underlying variable smoking. Now when pymc3 goes through the algorithm that generates the posterior, basically what happens is that for a given row, it goes through that row. If GDP actually has a value on that row, then the capitalized version of GDP simply takes the value that's provided on that row of the array GDP. Yeah, so nothing happens basically. But when GDP has a missing value on that row, capitalized GDP is going to randomly draw an observation from a normal distribution with mu equal to 0 and standard deviation equal to 1. Yeah, so for each time we run into this missing observation, we randomly draw from this normal distribution. And when we have, let's say, 2,000 samples in our posterior distribution, for a given row we're going to draw 2,000 different values of GDP for that missing value. Yeah, so it becomes clear to, when we generate the posterior, that this uncertainty that we have in this variable GDP, because we have missing observations for certain rows in that variable, we get that uncertainty back in our posterior. Yeah, because we're not saying that for this value we sort of impose the mean of the variable on that missing value. We say, okay, the only thing we know about GDP, if I don't have an observation, is that it's drawn from a normal distribution with mu equal to 0 and standard deviation equal to 1. So for each sample that we're going to use in the posterior distribution, I have a different draw from this distribution. Yeah, so it becomes clear in the posterior that there is more uncertainty than would happen in the case that we have observations for each row in GDP. Yeah, and the added uncertainty comes from the fact that since I don't know what the value of GDP is for that row, I have to draw it from this normal distribution. Yeah, and for each of the samples that I draw from my posterior distribution, I draw a new value of GDP. Yeah, so that uncertainty is going to be included in the way we're going to estimate our model, so in the way that the parameters are going to be estimated, and consequently in the way that we're going to predict. Yeah, so in our predictions, we're going to have wider intervals for the predicted variable y than we had before. Yeah, because not that we had before, than we would have in the case where we had observations for all the rows of GDP. Yeah, of course, before we also have uncertainty because we threw away a lot of information. Yeah, so that's another source of uncertainty. We had a lot less observations because we threw away every row in which there was one missing value. So we do this trick both for GDP, for smoking, binge drinking, high BMI, and for inequality. Yeah, so whenever we run into a missing observation for inequality, we draw it from this normal distribution with mu 0, standard deviation equal to 1, because we know it's a standardized variable, so the remaining uncertainty that we have about inequality if we have a missing observation is it's some value drawn from this distribution with mu equal to 0 and standard deviation equal to 1. So now when we specify our model, it's the same model as we had before, except that for these variables we use the version with the capitalized name of the variable. Yeah, so inequality, smoking, high BMI, etc. Yeah, so we don't need to do this for gender because we don't have missing observations for gender. So that's simply the variable that we used before. Yeah, so apart from that, everything is the same. Sigma is again drawn from a half normal distribution, parameter 1. We say mortality is mortality with mu equal to mu, so the one we specified here, and sigma. And observed is this variable log mortality, and then we start sampling from our posterior distribution. Yeah, so you can run this code. It takes some time to generate the posterior distribution, but not really much longer than what we had when we didn't use these missing observations. So simply run this code, and I'll leave it to you to generate the table. Summarizing the posterior distribution, check the R value for R hat, etc. So the only thing we're going to be looking at here is the trace plot. Yeah, so here we have our trace plot for our estimated model, and then specifically for the coefficients related to health. So the things that we're looking for is that this plot doesn't trend upwards or downwards. It has this condensed zigzagging. And all these features that we talked about before that these trace plots should have are actually satisfied in this case. So we're reasonably optimistic that the sampling procedure that we've used here converts successfully to the posterior distribution of our parameters, the B parameters that you can see here on the left hand side, the distribution of these. Yeah, so that's how you can deal in a better way with missing observations in a Bayesian model than either dropping the observation or imposing an interpolated value or the mean of a variable on a missing observation.